everybody to this TechTalk. So it's my pleasure today to introduce Aarne Ranta. So Aarne is a professor of computer science at Chalmers University of Gothenburg. His mission is to formalize the grammars of the world, and that is what he will talk about today.
Thanks, Johan, and thanks everyone for joining. Thanks, Michelle and Johan, for organizing it. It's great to be here. And now I'm going to tell you everything about a project that has been going on for over 18 years. And I will not assume that you know anything about it in advance. So this is my challenge today. Starting with the mission. So it's, of course, a paraphrase of Google's mission of making all information available, but it's a bit more specialized. So our mission is to formalize the grammars of the world and make them available for computer applications. Formalize means that we present grammars as machine-readable code. And there is a web page. It's an open source project, and it has been going on since 1998, when it started at the Xerox Research Center, Europe, in Grenoble. So, grammars. If you are inside natural language processing, so maybe you know that nowadays grammars are seen as something that requires a PhD in linguistics, and you have to work 5 years. Still, the result will be brittle, and therefore this is an obsolete technology, which has been replaced by statistics, where you only need a bachelor in computer science. You don't need to work 5 years, you just need to wait 5 weeks till the training has gone through. The result is robust, and therefore that's the state of the art in natural language processing. So why still grammars? And now I will show some bit provocative examples, but everyone who has been in statistical, especially phrase-based machine translation, will immediately know that these are genuine examples that are still hard, even for the state of the art in machine translation, the system that we all know and love. So grammaticality is the first thing that is difficult to get right. So if you know German, you see that the first translation is fine, but the second one is not right, because the agreement from the noun to the determiner doesn't extend across the adjective that lies in between. So this is a common problem with long distance dependencies that affects, for instance, n-gram-based models, but also many other things having to do with the sparseness of data and other things in the technology. And there are, of course, ways of solving this even in the statistical world, but I will show how at least recognize this as a problem of grammar. So now you might think that this is just a little cosmetic thing to get the agreement right here. It doesn't disturb our understanding the meaning, and maybe the languages will actually develop so that such things will be cleaned out, because it's just a nuisance for the learners of German, for instance, to keep track of this. But let's take the second example, which also has to do with the long distance dependency. So the first one, so umbringen is the verb for kill. And if there is an object in between, so then this is fine. But if the object is more than one word, so you will probably miss the connection between bringt and and then you get a translation which is not correct. Maybe even dangerous if you are, for instance, if you are spying someone's mail and trying to find potential threats for security. Third one, also related, coverage. So this is from my native language, Finnish, and you have the word for beer in 4 of the 16 forms that come from the number case combinations. And the fourth one here, actually this is not an uncommon form at all, but it is just was not given in the data. Although this is well known, so if you have a morphological analyzer, you would of course recognize this as a form of beer. So this is morphological coverage due to sparseness of data. And there's syntactic coverage, which is related, but a bit more kind of more difficult to solve maybe. So we like beer. We will not like beer, that should be. It's just a different tense of the same sentence, and then you form a question with the same things, and then you get something which is completely, yeah, let's say wrong. Precision here. So is there anyone who knows both Swedish and Chinese? This is an interesting pair because you see, even if you don't know Swedish, you see that these are two different sentences, and you have exactly the same sentence in Chinese. And what is the relation? So which one is any of those correct? Let's try the same example into English. Okay, still the same. So maybe this word inte doesn't really contribute to the meaning at all. But if you try with another noun, far instead of more, then you see that it actually, you might think that the inte is actually a negation, and that's what it is. So you might, when you see this example, so you might think that well, the translation seems to be correct, but here actually, well, what you get here is a translation which gives you an idea. It is about your mother and Swedish. So it does convey an idea, but actually it says the opposite what it was supposed to mean. And we still claim that grammars are one way of solving this. So why? So because we can understand grammars, we can understand exactly what's going on in each individual translation and also in the program that makes a translation. So the models are written by humans and they are human understandable and readable. You can inspect and understand them. You can debug them. For instance, if for some reason a negation is missing or a morphological form, and then you can recompile them, and you don't need to wait for 5 weeks, but you run the compiler for a few minutes and the whole system will be up and running again with the bug fixed. So the purpose for which we have been mainly using this is for domain-specific tasks. And this is a very, and maybe less problematic use for grammars. So you deal with a language where you only need to deal with hundreds or maybe thousands of concepts that you need to translate, for instance. For instance, someone's product catalog or something like that, very specific. And you can build your grammars so that you can reach rather high precision. And this is something that we have been doing with GF for many years. But then this is quite different from what for instance, the mainstream machine translation system are doing. So it's something where a consumer can take a web page and then throw it into the system and then see what this means in the user's own language. This system has to comply with or cope with millions of concepts, but typically the precision is somewhere below 50, if you think in terms of the blur score, for instance. And there is no system that can combine high precision with high coverage. And we have been concentrating on high coverage, high precision, because we think this is something that you can use in producer tasks if the system is not meant for a consumer who is browsing the web, but for someone who is publishing their information on the web and want to get reliable translations. And I will later say if we have time, so we will go into the consumer task in GF as well. But first, let's show an example of a producer task. So here is something that we did in the Digital Grammars company. So it's a system that translates technical descriptions of buildings from an accessibility point of view. and produces the web pages. And I could show many other examples, but that should be enough now. So that was, with the grammar, we can do this in a productive way, this kind of domain adapted precise systems, which are very multilingual, as I will also show. But the results can also be very compact. So we have a kind of a flagship of the project is the GF offline translator, which is a mobile app where you can translate among 15 languages. And it's available for both Android and iOS. It was originally for Android. And the colors, as I will show later, they show the confidence we have when we inspect how the translation was formed. So the level of analysis that you have. And all of this system is so compact that it actually fits on about 35 megabytes with the 16 modules for 15 languages. And I will say why it's 16. And at least, it used to be so that you can download Google or Baidu translator offline, but you get a much bigger system on board. And in practice, it's not very easy to have all of these languages on board at the same time. So compactness is maybe for the common people, so it's the most the clearest advantage of grammars, because they can compress the information so much, like orders of magnitude compared to storing, for instance, statistical phrase tables or even neural networks. Okay, but this said, I should also say that this looks nice with these examples, but on the average, Google Translate is still much better in terms of general overall quality. I will also come back to that. So, grammars are good, we want them. Maybe you are convinced by now. So, how we make them work? We still have this PhD and 5 years of work and so on. And I think this is very much due to the way in which grammars were viewed earlier. So grammars were seen as linguistic theories, where you have a huge definition of the grammatical sentence in English or something like that, as Chomsky declared the program. And they are big monoliths. Whereas, and nothing bad with that, so we have some very sophisticated grammars and formalisms that are for that purpose. But GF, to have a justification for existence, had a rather different starting point. So it was based on ideas from compiler construction rather than linguistic theory, because compilers are, of course, a success story for grammars. Yeah, all of the compilers have a grammar of the programming language, and then they analyze it, and then you get exactly the right translation into machine code. So we viewed them more like not definitions of grammaticality, because that's, I think, quite widely acknowledged to be brittle and very difficult to achieve, because all grammars leak. But the grammars are more like transducers. So they analyze the text and then they produce something. And this was also inspired by one of the well-known grammar systems, namely Xerox finite state tool that many of you might know. So it was exactly made in order to write transducers that do some specific tasks with the language. So that's why the whole GF is not a monolith grammar, but it's a framework for building grammars. And I think there are at least thousands of grammars that have been built, and for many languages, hundreds of grammars. The other group of lessons learned to GF was on the programming language side. So we see grammars as programs, and they should have a proper modern programming language, so that, for instance, you are not programming with copy and paste and maybe macros if you are very abstract, but you try to do something else. You don't I think I show this, is that you have functional programming, which allows a very compact and abstract way of writing grammars. There is static type checking instead of programmer's discipline, so that you know that your grammar will work at runtime. And this also supports distributed work, so that grammars can be built collaboratively with people who are not all experts. Whereas traditionally, grammar writing was very much expert PhD level work. So another thing which is kind of independent of this is that GF was from the beginning meant to be a multilingual grammar formalism, which fits with this transduction idea. Whereas traditionally, computational grammars were written as monolingual grammars for one grammar at a time, although there are some quite substantial grammar packages that have parallel grammars, but they are just, again, written parallel by the programmers having a certain discipline. So there is a book about GF that you might read in English or in Chinese. So what is the result? So we promised that you can go to the GF cloud. There is an IDE for interactive development environment for writing grammars in GF and publishing the results on the cloud as well, if you want. And you can get done in minutes writing your first grammars. If you start learning GF more seriously, then you will spend some hours in writing what we call the foods application grammar, which has some restaurant phrases. And this is not very far from what we have to a commercial application grammars, like the one that I showed about the accessibility database. So you basically write it for some days, at least for every new language. Going up in the units of time, so there is a full resource grammar, which is the one that gives you the full morphological inflection and a very comprehensive syntax, combination syntax, which typically takes a few months and typically is nowadays done as a master's thesis. And in between, there is mini resource grammar, which basically gives you a signature of each language so that you can do useful things with the language, but not yet quite in the full scale. So the resource grammar was meant to be a library to be used for these commercial application grammars and other academic application grammars. And in recent years, we thought that, well, this could maybe, the next step would be a wide coverage grammar, a kind of grammar which you can use in the consumer mode so that you can use it for analyzing and generating all kinds of text. And what is the expected unit of time here? I think this is, you might expect something here, and this will not be true because it turned out that we can build a wide coverage grammar on top of the full resource grammar in some days by adding two things. Adding a large lexicon, which we usually have obtained from resources like WordNets or Wiktionaries, and then adding some robustness into this, which I will come back to. So as a result, we have this grammatical framework community on different continents with more than 2,000 members, I think, and the coverage of different kind of coverage in different languages and countries. Here is a list of the languages that we have in the resource grammar library and in the wide coverage, and there are some in progress. And basically, why this has been so successful is that many people find this a very rewarding kind of work to, for instance, a computer science master student who hasn't thought about linguistics before, but who likes compilers and has learned them and likes programming, and then starts looking at his or her native language and then realizes, wow, this is very interesting. So a recent comment that I received is that once I got into it, it was obviously a lot of fun, a challenging task, which is also rewarding. And so grammars have been written by undergraduates, PhD students, professors, translators, hackers from many fields of expertise. I think in this order of frequency. So the most common one is computer scientists, and then mathematicians, and then linguists. We have had summer schools every other year that every time gather about 30 to 40 people, and we will have 2 summer schools next year, so to say. The first time we will have 2 summer schools. So if you're interested, please join. And now this was to be a technical talk, so I should tell you how it works. And I said it's modeled by compilers. So in particular, think about a multi-source, multi-target compiler like GCC to some extent, the GNU compiler collection. So you can have different source languages and different target languages, and what you have in between is the abstract syntax that formalizes the essential semantics that is common to these languages. And then most of the compiler is written in the abstract syntax level, and then you have a front end and a back end. And just to give a little example of how this task is, so if you are compiling Java to Java virtual machine, you have to do things like going from the expression on the left to this bytecode on the right. And if you know nothing about it, so it looks like a very difficult task. And the first thing you have to understand is word alignments. So which word in the source language corresponds to which word in the target language. And you see that here, and maybe you already knew it, that Java virtual machine is the postfix or a stack machine, so that you first have the operands 1 and 2, and then you have the 3, and then you multiply 2 and 3, and then you have the plus here. And of course, when the expressions grow more complex, these word alignments can become more and more messy, kind of long distance and crossing and so on. And how you deal with this in a compiler, so that's something that's called syntax-directed translation, where you have an abstract syntax tree, which is common to both of these notations. And then you know how to parse the expression on the left to the abstract syntax tree and how to generate the bytecode from the abstract syntax tree. Okay. And here is the first bits of GF code. So here is how you write it. You have separate abstract syntax and concrete syntax definitions. So in abstract syntax, you define functions. So add is a 2-place function that takes 2 expressions and builds an expression. And in the concrete syntax, you have linearization rules, which says how the abstract syntax trees are linearized into code by concatenation. So you concatenate the linearization of X with the plus sign and then with Y. And in GVM, you first have the first operand and the second operand, and then the byte for the addition. And this is the idea that we use for natural language as well. So we call it compiling natural language. We have abstract syntax, and then when we translate from Chinese to French, then we parse from Chinese to abstract syntax and generate French. And unlike in typical compilers, all of these translations are reversible, so that we can use it in both directions. So it's a decompiler at the same time as a compiler. So if you think of the translation task, which is to translate from every language to every other language, so here you see why it can be made so compact, because we just have the abstract syntax used as an interlingua. So the next thing is how we actually do this for natural language. And let's look at the very kind of the first rule that you learn if you are learning syntax in linguistics, which is that you build a noun phrase, you build a sentence from a noun phrase and the verb phrase. We call this function the predication. And then you build the verb phrase from a two-place verb and its complement noun phrase. That's called complementation. And the abstract syntax tree for John loves Mary comes out like this. So you have predication applied to John and the complementation to love and Mary. So this is the abstract syntax for John loves Mary in this kind of analysis. And then your challenge is how you, again, in traditional linguistics, so how you fit this syntax to the different word orders, subject, verb, object like in English, subject, object, verb like in Latin, or verb, subject, object like in Arabic. And you see that the abstract syntax tree was the same for all of the languages, but the parse trees come out quite different, and the word alignment also indicates this. So I think we know how to do SVO and SOV because this is actually the same thing as we did with Java and JVM, because SVO is the infix language and SOV is the postfix language. So we have a very similar linearization rules as we had for in the compiler case. However, to deal with VSO, we have to leave this. So what we are doing here was very close to what is known as synchronic context-free grammars. But now, in order to give the same abstract syntax for natural languages, it has turned out to be too weak a model. So we need something a bit more powerful than context-free grammars. And we actually add two things, which turn out to be just one thing under the hood. But the main idea is that the linearization doesn't only produce strings, but records. So when we build the verb phrase by complementation from a verb and an object, we do not put them into a string, but we store them separately in a record. And then when we use it in predication, then we can take them apart and put them together with the subject. And VSO is done. Another thing that we want to do is that different languages have different lists of inflectional forms, very different sizes. So English, for instance, has only 5 verb forms, and for regular verbs, 2 of them merge. And this is how you write the inflection table for the abstract syntax object love, which you might now think as the semantic object for the verb, for the word sense of love in its meaning that we use in John loves Mary. In German, I counted just that we generate 86 different forms because it contains all the participles that you might need. So a very different inflection table, but still the same abstract syntax, word sense, love for lieben. And in Chinese, you only need one word, so I. And of course, you wouldn't like to build your interlingual or abstract syntax in such a way that it makes room for 86 verb forms, because that would be complete nonsense for Chinese. But you just want to have the semantics in the abstract syntax. And by using these tables in the concrete syntax instead of just strings, you can make this possible. Agreement. Chinese is, again, very nice here. So if you say, I love her, it's wo ai ta. And if you say, she loves me, then it's ta ai wo. Okay, you just permute the words. But if you do the same in English, then you actually, no single word is retained, but you have to inflect all of the words. This is not a very rational language, but of course we don't want to change it, but we have to keep it the way it is. So we have to describe agreement in the concrete syntax. We don't need to make the Chinese grammar more complicated just because English has agreement. So we keep the abstract syntax with pred and compl, and we do the work in the English concrete syntax. So we have a table with the nominative and accusative forms for she and her, and then we have the agreement feature, which tells you what verb form to choose, and then the predication rules tells you how the subject agreement is passed to the verb phrase. And of course, there are languages more complex than English, for instance, German. So German has this basic variable word order where the word order is different in the main clause, in inverted clauses, and in subordinate clauses. And we can also deal with this in the common abstract syntax, but doing the work in the concrete syntax by using these tables and records. So basically, the main multilingual abstraction is that we have the abstract syntax, which has a tree structure, define the constituency and the word senses, and then we have the concrete syntax, which defines what the words are, what order they come in, how they inflect, and how they agree. And the abstract syntax is the same for the languages, and the concrete syntaxes vary. So to make this happen, we need, as I said, something more powerful than synchronous context-free grammars. Namely, we need parallel multiple context-free grammars, which are grammars over tuples rather than strings. PMCFG is a very nice formalism, so it's a mildly context sensitive. It's not fully context sensitive, but it still has a polynomial parsing, and that's why it's quite nice to use. But it's a very low level, so it's very tedious to write PMCFG grammars. There are some approaches where they are automatically derived from corpora, and we have also worked with those, but basically we have made it easy to write parallel multiple context-free grammars, which are can be quite subtle and quite complicated, but we solve this by using functional programming, static type checking, and a module system. And all of those are compiled away when you go to the portable grammar format, the PMCFG binary, that we actually can then put on the phone. I also mentioned type theory here, actually. That's what we use in the abstract syntax. So it's for defining different levels of semantic precision, and I will come back to that. But so it's not only PGF is actually, it's type theory plus this parallel multiple context-free grammar. And what did I have here? Okay, so we had this added expressive power compared to synchronous context-free grammars, which I think that was well covered. So you have inflection tables and records, which are then encoded as tuples in the PMCFG. So when you write your GF grammar, it has lots of modules, some of which you write yourself and some of which come from standard libraries. Then you run a GF compiler, which is a rather heavy program written in Haskell, running on a PC nowadays. Maybe in the future you can run it on your mobile phone, but the target is to get something that you can put on your phone, small enough for that. So that's how we use grammar. So when we ship the grammar product to the users, then it's in the form of the PGF, the portable grammar format. So the resource grammar library, the library that defines the morphology and syntax for over 30 languages. It has, the morphology is usually, for most languages, it's represented as so-called smart paradigms, where the idea is that you, like you do in grammar books, so they tell you very carefully what kinds of word suffixes generate what kinds of exceptions from the regular inflection, or what paradigm you use for a certain ending for words that have a certain endings. So we have this for the main parts of speech, and then you can build a lexicon by just giving one form. And this is both used for manual and automatic lexicon building. So for instance, if we're taking Wiktionaries, and they usually don't have, or not always, they don't always have morphological information, so we can infer most of that automatically by using these smart paradigms. More precisely, so depending on a language, we can infer up to 97% of the inflection tables correctly from just one form. And if we give another form, then we are always very close to 100. So it makes lexicon building even manually, but also if you extract this from data, so it makes it feasible. Then that was morphology, and in syntax we have combination functions. And for many users, for instance, we also, of course, have the spread and compl functions, but it can be more intuitive to use this function that takes the subject and the object at the same time as the verb. So this is one of the functions in the Resource Grammar API. And now, for instance, if you take apply this to he and I and the verb umbringen in German, which you have defined by using the paradigms, then you will get an inflection table for the clause, which inflects it in all different tenses and negations and word orders and so on. Tens of forms here. And there is an API documentation that we maintain by generating it for all of the languages included. And for instance, if you are localizing a social media saying that someone likes something, then this is how you do it for English and Swedish and Italian. And in Italian, you moreover have to switch the subject and the object, but that's no problem. So here you have an example of a semantic abstract syntax concept, like, which is more abstract than just saying that you have a sentence with a subject and the predicate. So when you have this, it generates you all kinds of possible uses of the like, which in Italian is the verb piacere, with different word orders and inflections and so on. So I wanted to show a little demo of the resource grammar now. And it's an incremental parser where you can write sentences so that the next word is predicted by the grammar. So these are like the fridge magnets, which you might know, but they change dynamically according to the grammar. So these are what I wanted to put here. The black cat sees us. Okay, and you can continue with some adverb or some other things. But now what I wanted to show is that you can illustrate the abstract syntax, which looks like this. You can see the word alignments, which look like this. You can also see the concrete syntax tree, which we show as a dependency tree. And now this is mapped to universal dependencies that you might be familiar with. It can be useful. Or you can also see the phrase structure tree. And then finally, you can see the full inflection tables of the sentences with all their tenses and other variations. So this is what you can play with, but it shows about the things that we can do with the grammar and how it works in a multilingual way. So now I was to say about this abstract syntax tree. So it is language independent, ignoring morphology and word order. Semantic, it's type theoretical lambda term, and it's non-lossy. It can generate the other trees and the surface forms. So basically, you can see parse trees or phrase structure trees and dependency trees as two different projections of the abstract syntax trees. And there are algorithms how you get the trees from the abstract syntax trees. So here is how you get the parse tree. So you start with an abstract syntax tree for the black cat sees us, and then you link it with the French words, and then you get the parse tree. And the dependency tree is a little bit more interesting. So if you have the abstract syntax tree, so the universal dependencies here correspond to different argument places. So for instance, the pred VP, you know that the subject is in the first argument and the head is in the second one. You annotate a tree, and then you can throw away the abstract syntax functions, and then you follow links for each of the words, finding its head, so that you get the dependency tree as a projection from the abstract syntax tree by throwing out some things. And you can do the same for French as well. So I don't go more into this, but we could say that there is a lot of in common in the kind of philosophy of GF and universal dependencies, namely that we want to have the same syntactic representation for many languages. And this is one of the main research directions that we are doing now. But this takes us to the last part, which is scaling up. So I said that we can reach precision with lower coverage, but actually we want to reach higher coverage by sacrificing some precision. And we do this in an interlingual way to keep the grammars compact and manageable and highly multilingual. So if you know Vacua triangle, so this is an adaptation of that to the interlingual setting. So the green translations use a semantic interlingua, the yellow one syntactic one, and the red one's chunking interlingua. So for instance, if you have my daughter is hungry, so on the semantic level, this is a predicate hungry, which is then applied to possessive of I and daughter. On the syntactic level, this has an adjectival predication, my daughter and hungry. And on the chunking level, it just has some chunks for each of the words. And if you translate from these abstract syntax tree compositionally to French, for instance, in the semantic translation, you get a nice translation because it actually doesn't translate word to word or structure by structure, but it says that my daughter has hunger. Whereas using an adjective as in the yellow translation is a bit awkward. And then in the red translation, you even lose the agreement. Basically, you use this for different parts of or different sentences. So the translator always tries to find the best level of translation. And here are some examples of what you do. So for instance, I think the yellow translation of here is particularly strange because it's something that is grammatically correct, but it really doesn't give you the right sense. And I will not show a demo of this. I would just say that we are below state-of-the-art statistical machine translation on the wide coverage segment. Of course, we are working on that at the same time as we are, of course, also working on the other levels. And here is another little piece of evaluation where we saw that in the semantic level, we can do actually quite well, whereas there is another evaluation from a free text where we do much worse than the state-of-the-art statistical machine translation. Maybe the thing that we find cool is that we can do this at all with grammars and even in the device such as a mobile phone. Here are some other blur scores from our commercial case with the accessibility database. So to come back to the translation, we would say that GF has these advantages of guaranteeing grammatical correctness. It has feedback with trees and colors. It's less dependent on language data. For instance, we have all of the inflection forms of Finnish words, although there is certainly no corpus where they all occur. And the multilingual systems can be made compact in size, whereas we are way behind in non-compositional idioms and in contextual disambiguation. And these are cases for hybrid methods where we are also working on. And the future trends are that we, of course, there is more and more interest for this controlled language or the producer quality tasks like localization, text robots, data-driven documentation, precision translation, and also some business. So that's why we started the company. And on the research side, you have this hybridization where you can think of a GF-driven hybrid where you have a better statistical disambiguation than what we have had by now, and also grammar writing automation by machine learning and other methods. Or we also hope that people working on statistical frameworks might be able to exploit GF. For instance, there is an idea of using a factored model on abstract syntax, which should be quite general. And then there is with this UD, universal dependency, so we have used this for bootstrapping tree banks for languages where there is not yet a tree bank, because we can take them, for instance, an English tree bank and just translate that to another language tree bank. So I will not show this example. What is still to accomplish is to formalize the grammars of the world. We are constantly working on more languages, wider coverage, better quality, and then usability in other contexts and framework. The take-home points. So GF is for grammar engineering without tears. It has multilinguality via abstract syntax. The model is compiling natural language, and an application is interlingual translation, in particular via domain adaptation to reach high quality. And we currently provide languages for a bit over 30 languages, but this is growing. And most of this stuff can be found on the Grammatical Framework webpage. Thank you. You sharing?
Yeah. You started by showing some examples where the statistical approach is typically right. And I think you mentioned an abstract. What types of problems the your approach has? Give some examples. Like some typical examples, yes, where you fail.
Yeah, so I have prepared this. I just took a random text. Well, first there are two phrases that are very good, but then I took a random text from our course web pages, and you see all kinds of problems here. So one is lexical coverage. We didn't have the, for any reason. Okay, so here is two problems in one. So there was something unknown, and therefore select was treated as an adjective erroneously, and all of the translation just goes completely bad. This I thought is quite good, but there is one word missing from our lexicon, just randomly. And again, so you can see there is, on the bottom of this, there is try Google Translate, and I can promise you that it will be much better than what we had. So I mentioned that there is one particular thing, which is a disambiguation, where we do not so well. But the other thing is very much kind of random things missing from here and there in the lexicon.
Can you tell us how we deal with ambiguity in our system?
Ambiguity, yes. So we deal with it by basically we are let's have an example. Okay, oh, this is a bit strange. So you basically have different syntax trees that gives you different translations. And here, for instance, the U has 3 possible translations in German, and we display them all, and we rank them statistically initially. But again, if you are working in a production task, then you want the user to be able to pick the right translation. So the last mile is interactive, but before that we have some statistical ranking.
Do you have some way of specifying sub-grammars? Like you showed this example with the inflections of the verb log in German.
Yes.
But couldn't that be specified as one of the grammar as like verb extend followed by some postfixes that are the same for all verbs?
So what was the first word? I didn't hear the beginning of your question.
How to specify in your grammar?
Yes.
Grammar structure at the subtoken level. Like
Subtoken. Yeah, so basically we technically do everything into tokens, like umbringen. So we have 2 tokens. Right. And then when they are glued, like
dass mich umbringt. Then there is an analyzer that detokenizes it. So it's a part of the grammar, or it can be a separate process. We have used both approaches.
I mean, the grammar is not limited, it's just that you can use it either with a long table of all the variants of the
Yes.
verb, or by chunking the verb into pieces.
Right, right. So this is actually what we do in Finnish, that we don't generate all of the forms because there are so many, and to store them even in a compact with some compression would be expensive. So we actually divide them into tokens, and then we use those with some penalty in the speed and maybe in ambiguity. But anyway.
Another question about syntactic parsing. You mentioned formalism might be sensitive. So CCG and Johnny Grumberg, they either use the formalism as a way to capture phenomena like crossing dependencies, or they use some kind of a number automata like embedded push. How does GF like crossing dependencies or scrambling?
So you can do this by using the records and putting different parts of the sentence that may turn out to be a part. So you put them in different fields in the record, and then you combine them. So I think we have dealt with most of the classical examples and give them as exercises to students, because it's very good to look at those and make sure that we can deal with them, and that each new grammarian knows how to deal with them. But it's quite straightforward, I would say, in most cases.
Any more questions? I thank the speaker again.
Thank you very much.